Hello there. Welcome to our today's science lesson. The topic for the day being history of elements. In our previous lesson and lessons, we talked about various particles and the most dominant one being an atom. And having looked at that atom, we discovered that this atom makes what you call an element. If there are more than one, then we can come up with other substances or particles which can be in molecular form. However, even if it is in molecular form or even in a bigger substance where there are so many atoms together, the most essential part of that substance will be a small particle by the name an atom. We also defined an atom as the smallest particle of an element, and we further went and looked at an element, and we saw that an element is that smallest particle that is made up of only one type of atom, where we give examples like I can say O standing for oxygen as an element called oxygen. We can say S as a symbol standing in for sulfur as an element, and in that sulfur, in that oxygen, in that ion, it can be an nonmetal or a metal. The smallest particles we will be talking about are atoms, which in essence are just elements. So in this lesson, we want to look at how the development was done to come up with the so many elements we know by now. We said in our previous lesson we have a total of 118 elements which are well arranged in a periodic table, and out of the 118, 92 can easily be found at any single moment because they naturally occur. But the question comes, how did all these elements come to be discovered? And after they have been discovered, where we saw the development of how the elements came in, another question comes in. Yes, you have discovered the elements. What makes one element to be different from the other? It means you are talking about those atoms of those elements being different from one another. What makes realistically that element be placed where it has been placed in the periodic table? Those are some of the questions we need to answer in this lesson. First of all, we need always to realize that anything you are seeing right now, however complex it is, however nice it is, whichever way you look at it to be more advanced, at one time it was an amateur of what you are seeing. It wasn't as complicated as what you are seeing. It wasn't as advanced as what you are seeing. And the explanation behind it wasn't as advanced as what you know. At least there was a starting point. And that starting point, at that very moment when that starting point had been initiated, that was the most advanced information, knowledge, or working of that particular item, substance, system, statement, or whatever case we are talking about. Today, we want to look at, in these elements, how was an atom identified? How was it found that this is an atom and this is how it is made? This is what it means. At present, we may be knowing a lot about an atom, knowing that it has two parts, the innermost part, the nucleus, which carries much of the weight, and the outer part. But how did it develop until it reaches the today's information we know about an atom? So many years back, that is around 4060 BC, this is when some of this work began about an atom. In that era of around 4060 BC, early Greeks, most of the scientists by then were Greeks, they came up with an idea of what is an atom. By then, they were not calling it an atom. They only call it a small particle that encompasses what we call matter. As we said, matter is made up of small particles, which can be, because of the different properties around it, can be in solid, liquid, or gaseous state. But this matter, which now we are calling atoms, was discovered at a particular slow pace by some of these scientists, the earlier ones being the Greeks, who were then followed by the alchemists. Alchemists, these are a special group of chemists who are like semi-chemists. So we call them alchemists, who did also some good work on developing what is an atom in terms of what it contains. In the early Greeks, they came up with a description of an atom as one, that all matter, just like what we mentioned earlier, that all matter is composed of atoms. Those small particles are called atoms, and these atoms are small units, small bits, tiny bits that cannot be divisible any further. Being that they cannot be divided any further, then it means all the substances on earth, all the items, in a general, matter is made up of small, tiny particles by the name atoms. And they also said that there is a void between these particles by the name atoms. So if you have this an atom and this an atom, to the early Greeks, there is some kind of space between the small particles by the name atoms. There's a void, a space. Why they imagined that there could be a space between is because of how some matter can be changed from one state to another, or from one form to another, meaning that there is some kind of freedom, there is some kind of space that will allow manipulation of these small particles by the name atoms. And that's why they called a free space, a void between the atoms. They also say that atoms are solid materials. The atoms are completely solid. They are not liquid, they are not gaseous, they are just solid. Though they are small, but they are just in one particular form, and that is in a solid state. Some of these facts, as we are looking at them, may be true up to the moment, and some may be false, as we shall be discussing further about them. The early Greeks also discovered, discovered that matter is made up of homogeneous atoms. Homogeneous atoms of its internal structure. Homogeneous means just one type. One type. Just like you can say iron bar. If you talk of an iron bar, a metal, iron metal bar, like maybe this way, to them, inside this metallic bar, it can be another element. I'm just using iron as an example. Inside here, those small particles, which are now ion atoms, will be the only ones possible to be found in that particular material, or in that particular substance, or in that particular piece of matter. So the small particles are homogeneous, and that is in the internal structure. And they also looked at an aspect of size, looked at shape and weight, and came up with an idea that in this type of matter we are talking about, if you look at iron, these are metal, go look at aluminium. I use chemical symbols now that at the moment we all now know that all elements have their chemical symbols. So if we have iron, we have aluminium, these are metals, I have sulfur, and I have maybe phosphorus as nonmetals. For these early Greeks, they saw that in terms of describing these small particles that are forming these phosphorus, or this sulfur, or this iron, or this aluminium, we have to realize that they will be different in terms of shape, in terms of size, and in terms of mass or weight. As I have said earlier, that some of these facts may be true, but some may be false as we continue, or even at the moment, probably the information you already know. You will discover that some of the things that we are going to be mentioning will be false because of the high advancement that we are in at the moment. But some are right. Like, let's look at this. Is it true that atoms can vary in shape? Is it true that they can vary in size? And is it true that they can vary in mass? The answer is yes, they will. Looking at iron, the size of iron, and looking at the size of sulfur, automatically they will be different because of what that atom has inside it. The number of the particles that form an atom in sulfur and iron, aluminium and phosphorus and all the other elements will obviously be varying. And because of that, you'll discover that the shape of the atom will vary. Later on, because of the difference again in terms of the number of the small particles found in the atom, the size will also vary and the mass will also vary. And that's why you can find that aluminium is more favored in making some structures since it is lighter and strong, but iron cannot be favored because it is heavy. We are looking at this. But remember, we know this because of our present advancement in technology. By then, these early scientists didn't have some of the advanced technology we have to realize some of this. And to them, this was a proposal of what they think an atom is. What does this mean? This means that there are so many scientific facts that we know today, which as at now, we shall always conclude that is the best, that is the most right information we know about something. But science is about trial and advancement. Trial and advancement. So as we go on doing more trials on whatever thing we are doing, and one of the things that are still doing trials is on an atom. Because there are so many things that are being discovered, being made, which for you to understand them very well, you have to go down to an atom, the smallest particle that is being used to make that item. So you'll discover that so many years to come, the atom the way we know it today will not be the atom that will be known by that time. The same to these scientists, that is what has been done. An earlier scientist, for example, Democritus, I mentioned him earlier, in the development of the kinetic theory of matter, and so in so many other ways, he was one of the scientists, early scientists, and in early years of 440 BC, again, they also described atoms in different ways. They looked at the so many substances, type of matter that has been made, that is existing, that they are interacting with, and they saw surely that matter is different. And since from what you have just looked at, that atoms as the smallest particle in that matter can be described in so many ways, as we have seen, voids in between, it is the smallest particle, it can't be divided any further, it is homogeneous, and all that. They saw these materials that some are smooth. Where you are seated, if there is any smooth item, touch it. Feel the texture. Is it really smooth? Why? Identify another one which is rough. So you can also look at roughness. An item that is rough. Look at one that is strong. Strong. Maybe if you try to bend, it can't just be a bend. There's one that is weak. There is one, not that it is weak, but is flexible. There is one that is rigid. It might not be very strong, but rigid. For it to bend, it can't bend, like glass. Glass can be very rigid, but is not as strong as an iron bar to resist being broken. So it is rigid. And so many descriptions. So these early scientists, like Democritus, and that is in 440 BCE, that's so many years ago. These scientists looked at atoms as the smallest particle of these substances we are talking about, and tried to reason out what could be the reasons why these properties, this behavior of items is existing, and yet we are just still talking about the very atoms that we are now saying they may be homogeneous in that substance. We have some voids, they are the smallest particle, and so on. Then they came up with some explanation which as at now is wrong, but by then that was the explanation. For something like the one that is strong, they imagined between these atoms, we have atoms that have so many hooks on them. So you can imagine if this is an atom, and we assume each one of them has hooks. So they vary in number of hooks. The number of hooks can vary, which is at the moment is false, but by then that was the imagination. So they imagined these atoms that have so many hooks will obviously make stronger bonds between them. And by making stronger bonds between them, they make the substance to be much, much stronger. And for those that will have fewer hooks, maybe will make a weaker structure, which of course is wrong. They also looked at something like roughness. Why should this material be rough and another one to be smooth? They imagined the atoms making that substance that you feel is rough could be rough on the surface. So you can imagine an atom that is crooked on the surface. So if we have atoms of this type being homogeneous, which means only this type of atoms being packed together to form that particular substance, then the surface of that substance will end up being rough, which again, that is false. For smoothness, why should you imagine that substance is smooth? They also imagined the atoms forming such a substance should be automatically smooth, so that So many of them being together, maybe if it is oval but very smooth. So many of them of that kind, smooth, packed together, make that matter homogeneously, then they make it to be smooth, and so on. Of which, as I've said, all these way of describing why some materials are weak, some are strong, some are in solid state, liquid state, and liquid state, and gaseous state, is in terms of this type of description is wrong. But it is because of this wrong information that now more scientists had to come in, do more trials. As I've said, science is about two things: trials and more trials, then advancement. As you try, discover a new thing, advance on whatever you have. So more advancement was then done on this. The other advancement, or some bit of advancement that was done in 1700s. Now this is a bit more realistic advancement that was done, that is in the 1700s. In the 1700s, these are mostly the alchemists. The alchemists, the ones I've been mentioning, these are Greeks who did that. But the alchemists who existed in the 1700s did a little bit of more advancement on what we know in the early days. They looked at this atom as having a material that has two regions, the inner and the outer part. So they looked at matter as something that will always have the inner part and an outer part, which in a way it is coming to agree with how roughly we know the atom the way it is. But still, on their way of explanation, they will be a little bit away from the truth. So for the alchemists, after discovering that the theory they have is also agreeing with some of the aspects we have seen earlier, they developed a way of arranging elements. They developed a way of arranging these elements. Because remember, we have said that atoms are the smallest particle. These atoms, for them to form a particular matter, they have to be homogeneous. So you can talk of substance A that will have a particular homogeneous type of atoms, which means that is a particular different type of atom, that is an element. We shall also have a B, a C, a D of the same. Then they had to look for a way on how to arrange these elements in a particular systematic, agreeable manner, which was very helpful, because in the arrangement they discovered that there were some spaces that were being left. Just like, for example, if I can give you numbers like 1, 2, 4, 5, 7, 8, 10. Then I ask you, these numbers are not arranged in order. So let's have it like 8, 5, 2, 1, 10, 4, 7. They are not arranged in order. At first you may think all the numbers from 1 to 10 are present. But if you start arranging these numbers in order, then you will realize there are some gaps that are going to be left. Let's try. If these are the numbers, and you are asked, can you arrange them in order, in a systematic order, then you can do it as 1. So 1 is present, 2 is present. I expect to have a 3. In this one, I can look for 3 and I will never find it. So what are we seeing? There is a gap there. 4, because 4 is here. 5, because 5 is here. 6 is missing, so there is a gap. 7 is present. 8 is present. 9 is missing, there's a gap. Then we have 10. So this is what they did. On doing this, they had now to ask themselves hard questions. We shouldn't have gaps. We must always fill the gaps. And since all these others are present, then it means we haven't done enough. We have to do enough so that we can come in and make sure that these missing spaces are no longer existing in our table. Because of this, it helped them in identifying and discovering new elements. It helped in them identifying new elements that was used to fill in the missing elements. However, they didn't have so many elements. This opened a window for another serial scientist who is even mentioned up to now as Lavoisier. Lavoisier was a scientist who now came in systematically to arrange the elements, at least using a more reasonable way of doing it. And by saying a more reasonable way is you use the same basics, the same standards on A, B, C, up to all the elements. Because for the others, they used things like the mass, of which at present you may realize that we have atoms that can have the same mass, but they stand in for different elements in what we call isotopes. If you have isotopes, you'll discover that two elements can have the same mass. So just using mass is an issue. So to this scientist, Lavoisier, he used both mass and other aspects like even the characteristics of that element when it comes to reaction. Now, when I talk about a reaction, that is a new issue by then. That is a new issue. Because to this early scientists, the early chemists, they saw that matter is only made up of mainly 4 things. And that is fire. Matter is made up of fire. It is made up of water, made up of air, and made up of the earth. The earth as it is. And if you look at it, surely this is very wrong. But to them, matter was made up of this. So everything that we have here on earth was a mix-up of any of these in whatever ratio. But the coming in of Lavoisier, he discovered that no, matter and how it changes from one form to another, from one set to another, is not just an issue of rearranging these aspects of small particles called atoms in either fire, water, air, or earth, but is an issue of reaction. Is an issue of reaction. So the change of substances from one form to another is not a rearrangement of just the atoms, but is an issue of reaction. How did he come up with this? He did an experiment of heating a tin can for a very long time until no further ash was being formed. And this tin can was closed. If you can have a container like this, maybe it is open, then you seal it, and you have something inside before sealing. So inside here we have something, and that is tin. And you are doing strong heating. You do the heating until no further change is observed. Only ash is formed. No any other thing. Ash is formed, meaning that everything has been completely consumed. Then the scientist opened this container in water. What he discovered was water rushed into the container because it was in a controlled manner, such that it is only if there is space left inside that will allow water to go in. If there is no space left inside, then water will not move in. It means no vacuum that has been created, semi-vacuum. But if it moves in, then there is a kind of a semi-vacuum that has been created. So he discovered that water rushed in to fill around a fifth of the container. What was his conclusion? His conclusion was air, as was seen as a component of matter, was no longer as a single component, but is a mixture of components. So he came up with a conclusion that air is not as people imagined, that is just made up of one component. It is made up of a mixture. And why? Because part of it had been used in a reaction and part of it was left. Meaning that the one that was used in a reaction is totally different from the one that had been left. Sorry. So at that point, and that is in 1700s, is when all of these came out clearly, that surely the way matter is being perceived is not the way it is. So this opened a window for further trials, further investigations on whatever had already been discovered, and it gave out to more advancement, as we will be seeing as we advance with our lesson. Now, the story we have just heard, this is of the early chemists, and that is in 1700s. There came another period, and that is in the 1800s. This time, at least, a lot was done. A lot was done on atoms, and it was mainly done by one of these scientists by the name John Dalton. John Dalton came up with another way of describing an atom. So we are talking about John Dalton, who came up with another way of describing an atom. Though in some of his description, you will find that part of his description and the description of the early scientists in Greece, the Greek scientists will be agreeing, but some will not. And also you'll discover that some of his description of an atom are still being carried up to today in a way. So we can say this is like a good link between the early and the present way of perceiving an atom. So John Dalton, as one of the modern scientists, developed a modern theory, atomic theory, which is partially also being used up to today because it still carries much importance and truth in it. To him, he said that elements are made up of tiny particles. Elements are made up of tiny particles, and the tiny particles are atoms. Elements are made up of tiny particles, and those tiny particles are atoms. If we can make an overview of what we have just mentioned earlier on the Greek scientists, they also talked about the same. They said matter is made up of small, indivisible particles, and these are atoms. John Dalton also has mentioned the same, that matter is made up of small, tiny particles, and these particles are atoms. Atoms of a particular element are identical. Atoms of a given particular element. If I say an element, for example, zinc as an element, then the atoms in this zinc will be identical. If you look at it also, it is agreeing with some of what the Greeks said. For them, they didn't use the word atoms being identical, but they said they are homogeneous. They are homogeneous. Homogeneous means one particular type of that substance. One particular type of that substance. So here, if it is zinc, we only talk about zinc atoms. So we can see they are agreeing already in two, but it's only the way of describing it that is varying. The third one is atoms of a particular element. Atoms of a particular element will always vary in mass. Atoms of particular elements will always vary in mass as long as those elements are different. Look at zinc. Maybe look at iron. These are two metals, but they are two different metals. From Dalton's theory, the atoms in zinc and atoms in iron must vary in terms of mass. So the mass here must be different. Why? Because when you look at the mass of iron and you look at the mass of zinc as a metal of the same size, they will be varying in weight. Meaning that the small particles in them that are making up that zinc bar or iron bar must automatically be different in terms of mass, of which it is also true up to today. If you find this substance is different in mass from the other one, then it means the small units that are making those different substances will automatically vary in terms of mass. He also came up with now going by what we saw in terms of reaction. What we saw one of the scientists doing that is a Democritus, who saw a reaction using tin and saying air is no longer air as people perceive, but is a mixture of other materials, which at that time he didn't mention, but he at least said it is a mixture. So for John Dalton, he now saw a reaction which came out to give out compounds. So to him he said compounds are formed by a combination of atoms, the small particles. Compounds are formed by a combination of atoms. And these atoms being small particles and them coming together to combine will obviously come up with new different substances which he was calling compounds. And looking at the issue of compounds, you can also realize in the present world, chemistry or science in general is about reactions, and in those reactions we always have atoms, which are the small particles, coming together to form compounds. Looking at our previous lesson, we were using shapes to combine with others. This meant an atom, this one was also an atom, and these two have come together to give us a compound. So this one is also agreeing with John Dalton, and in fact that's why he was taken to be the scientist who gave the modern theory of the atomic, the modern atomic theory, modern. Though it is in 1800s, but at least from his description, since it was still agreeing with what we have today, then it is taken to be the modern atomic theory. Then you also said that atoms cannot be created. Atoms cannot be created nor destroyed in a chemical reaction. When you have atoms, you can maybe change them from one state to another. So you can talk of state. You can change them from one form to another. So you can talk of the form. And maybe things like shape. And so on. But essentially, according to John Dalton, atoms, which are the smallest particle of matter, cannot be created, neither can they be destroyed. They can only be transformed to form other things, which in a way, looking at our present science, it is true. If you want to form water, you can burn hydrogen gas in oxygen gas and you will get water. Looking at this water and looking at the reagents, what you have only done is you have changed the way you have connected the small particles of this gas, which is hydrogen, and the small particles of this gas, which is oxygen. But you have not created a new hydrogen nor a new oxygen. What you have only done is you have transformed, and by transforming, you have changed the shape. And by also this transformation, you can easily change the state, and you can even change the form. And these forms a compound. So in formation of this compound, it is agreeing with what John Dalton said, that compounds are formed by combination of small particles that are found in matter, and the small particles are atoms. And lastly, he gave a recommendation that chemical reactions, which we saw in the first part, was seen when we were talking about heating the tin can, that chemical reactions changes the way atoms are grouped. Chemical reactions changes the way atoms are grouped together. Now, is it true that chemical reactions can change the way atoms are grouped together? Yes, if you are able to explain, and no, if you are not able to explain. Let's look at this reaction. If I have, may I use the very one I've just used, that is hydrogen gas plus oxygen gas as a reaction. We are burning this hydrogen gas in oxygen. Can this reaction lead to change in grouping of atoms? Because our product here is now water. The answer is yes. The grouping of atoms here was only hydrogen atoms were present. Hydrogen atom plus hydrogen atom gave us hydrogen molecule. So we have so many of the hydrogen molecules being called now together as hydrogen gas. So we can call this one hydrogen gas. The same will happen to oxygen. So the grouping is hydrogen atom together forming hydrogen molecule. So many hydrogen molecules giving us what we are calling hydrogen gas. So many oxygen molecules giving us what we shall call oxygen gas, and so many other reagents. But now, because of the reaction that is going to take place, look at the group we have formed. Does this one look like this? Or does it look like this? It doesn't look like any of the two. So what is the conclusion? It is true that chemical reaction leads to formation of changed compounds in terms of grouping. Changed compounds in terms of grouping. whereby you can now see two atoms of hydrogen being grouped together with one atom of oxygen. Let's look at another one. You have an alkaline solution like sodium hydroxide reacting with the hydrochloric acid. Let's look at the grouping of the atoms. The grouping here, you can see we have one sodium atom, one oxygen atom, one hydrogen atom. Here we have one hydrogen atom, one chlorine atom. For these to react, it will give us a different grouping, and that is sodium will take chlorine, and oxygen, hydrogen, and hydrogen will group themselves together to form water. This is a chemical reaction. Looking at the statement John Dalton gave, which is the last one, that chemical reactions change the way atoms are grouped, it is true. This chemical reaction has changed the way the atoms have been grouped. We had 3 here, now we have 2. We had 2 here, now we have 3, because here we have 2 hydrogens and 1 oxygen there. So that is a real agreement with the present science, just like it was those days in 1800s when John Dalton was doing his work. Now, though the early chemists did some arrangement of these elements so that it can help them at least to identify some elements, as I said earlier, they didn't go far. However, in 1869, Dmitri Mendeleev, a scientist, now did some good work on some of the atoms that had been identified by then. Some, as we have seen the way John Dalton was describing, some had been discovered, and that's why he was working on them, so that he discovers what he has given us as our modern atomic theory. So Dmitri Mendeleev did an arrangement of these elements, and mostly by then, as I said earlier, was based on mass. And by this mass, he arranged these elements in columns and rows. You can have such a thing. He arranged these elements in columns and rows, and by doing so, he also now saw what we also discovered earlier when we were arranging those numbers of ours. We discovered number 3 was missing, number 7 was missing, number 9 was missing, and you can only discover that if you arrange, and not just arrange, but arrange in an orderly manner following a particular sequence. And in doing so, after you have discovered what is missing, you may work more harder to discover what is it that is missing in that particular space. So some of the elements that were discovered were so unique, but he also came out to discover that in addition to what he has done in terms of arranging, he discovered an atom has a particular characteristic. An atom has a particular characteristic, as he was studying the masses of these atoms, so that he can be able to arrange them in these columns in order, for that matter. He also discovered some characteristics of this atom, that an atom has an inner part and an outer part, and the mass of the atom is centered at the center point of that atom, and the outer part is not so important in terms of mass. He also looked at the size, because as he was arranging these atoms in terms of that mass, size will obviously come in, whereby you'll have to see, oh, this one is small, but it has so much mass. Or this one is big, and it also has so much mass. So size also comes in. And in that size, he looked at an electron in relation to an atom. Electron in relation to an atom. And this electron was the one that was making the outer part of this atom. So an electron in relation to an atom, so electron versus atom, and he discovered that an electron is very, very small than an atom. And the atom he was talking about was a hydrogen atom. By then, he was working on hydrogen atom, which was about 2,000 times smaller than a hydrogen atom, the size of an electron. Because of all this, as we have said, trial and development. Because of all this, other scientists now picked from there. They really wanted to see. Now, an atom was the smallest indivisible particle. But now it is coming out to be seen, it also has some parts. It has an inner part and an outer part. This outer part is having a small particle, which now is being called an electron, which is much, much smaller than a hydrogen atom. So another scientist, Philip Leonard, that is in 1900s, Philip Leonard in 1900s, that is Philip Leonard, now did an experiment of shooting electrons. Now that they have been discovered, he really wanted to know much more about these electrons, the new things that have been discovered, and they were once never known to be existing, because an atom was just one solid particle. Remember the Greeks and John Dalton? It was just one solid particle. But here it has been discovered that this small solid particle has something in it by the name electron. And he shot those electrons on an aluminium foil. So shooting on an aluminium, which is metallic, aluminium foil is a metallic. So the scientist Philip Leonard shot electrons on an aluminium foil, which is a metal, and in so doing, other things came in, other discoveries came in. He discovered an atom is made up of two parts, negative and positive. Because being an electron being shot, it will obviously create a change in the way that aluminium is being or is responding, because electrons, as we know today, they are negatively charged. By then, that electron was not known to be negative, but it was shot. So after being shot on that aluminium foil, then the response gave out a conclusion that atoms have negative part and they also have positive parts. This also led to another scientist who looked at it, that is Niels Bohr, who did a further test on a gold leaf. A gold leaf where the tips is divided, and on top we have a plate that can be charged. You can make this one charged, maybe negative, and you pass by maybe a positive item, and see what will happen to this other part. So if you have made this side to be negative, this part will be positive. If you make this one positive, then this one becomes negative. So if this is negative and you pass by the positive, before splitting, the leaves will be close by. That is before splitting. But because the charges are well spread. But when you pass by the positive, it will attract the negative but repel the positive. When this positive will come to this other part positive and also come to this part positive, positive and positive will repel, and the next will be now the leaves will be separate. This was just to confirm that surely whatever you are having around this gold container is charged. This charged particle could be of any, like an alpha particle, which is helium. Alpha particle was used, which was helium. In so doing, it gave out a confirmation that surely an atom is not just an atom as previously known, but it is a particle that has other units in it. Later on, it was also discovered that, and that is by Rutherford, that is 1932, he did other experiments, and that is also by James Gatwick, did an experiment where now a neutron, a third particle, was now discovered. A neutron was now discovered, and that is in 1932. After the identification by Rutherford, then James Gatwick also did an experiment where now a neutron was discovered as the third particle. After having discovered that we have positive and negative, and the positive was called a proton. The positive was called a proton, and the negative was called an electron. But on looking at the masses and the positive aspect, there was an imbalance. Mass was higher than the positivity in the particles. So it meant there was something else that is contributing to mass, but is not contributing to the positivity of these atoms. And on doing the experiment by the James Gatwick, he came out with a neutron as the third particle, which now concludes our particle by the name atom as having subatomic particles, which are protons, electrons, and neutrons. But remember, it was also seen earlier that as much as an electron is there, where we saw it is 2,000 much smaller than hydrogen atom, this electron is found in the outside, and in the inside, therefore, are around the other two particles as we know it today, and that is protons and neutrons. We have talked about how an atom was developed so much. Just an overview using questions to see how much you have gotten would be a good idea. And let's look at just one question. In our next lessons, we shall also look at so many other ways on how we can revisit or review the same as we proceed with those lessons. So a question for today: in what ways were the atomic models of Democritus, remember that is in 40, 60 BCE. So in which way was Democritus and Dalton similar? Dalton and Democritus. John Dalton is taken to be the modern scientist in terms of the theory, but we also have Democritus, who in 40, 60 BCE also came out with some recommendation on what an atom is. Number one, we looked at matter, and we saw that matter for Democritus is made up of small indivisible particles. But John Dalton also gave out the same, that is made up of small indivisible particles called atoms. So at least on that one, they agreed. They also looked at a substance, that matter, the type of small particles in it. For John Dalton, the Democritus, he said the small particles which are atoms in a particular element, they are homogeneous. For John Dalton, he also said that the atoms are identical. Remember, there are those areas that they didn't agree, but at least on those ones, they agreed very well. In terms of matter, what makes that matter, and in terms of being identical and being homogeneous. That marks the end of our lesson today. Much more will be done in our next lesson about the same. Thank you.